So here is an exercise. We need to negate statements. So the way to negate statement is as follows. When we negate a quantified statement, we negate all the quantifiers first, from left to right, keeping the same order. Then we negative the statement. So, example. Here we have this statement: for all x in A, P of x. The negation of that statement is there exists. So for all become there exists. There exists x in A, such that not Px. Not Px. So for all, negation become there exists. There exists become for all. And here we have the original statement is there exists x in A, P of x. The negation is for all x in A. So there exists become for all x in A, not P of x. That's all. And here we do from the left to right. The original statement is for all x in A, there exists y in B such that P x y. The negation is there exists x in A, such that for all y in B, not P of x. Alright, we just change from for all to there exists, from there exists to for all. The statement becomes the negation. Another example: there exists x in A, for all y in B, P x y. The negation would be for all x in A, there exists y in B such that not Px y. And the last rule is the negation of a statement if P then Q is P and not Q. One way to explain this, say we remember we have P implied Q is equivalent to what? Not P or Q, right? We did prove that. So the negation of this one is the same as the negation of this one, right? And the negation of this one is what? Not of not P, so it's P. Or become N. Q become not Q. So the negation of P implied Q is P and not Q. That's how we remember it, or how we explain it, say. Okay, so here we have 5 rules to negate a statement. Basically it just we do it from left to right. For all becomes the exists become for all, and this implication rule. Okay, let's do an example. Let the allowable values of x and y be the real numbers. Consider the following statement: for all x, there exists y such that x bigger than y squared. Okay, let's just write down in terms of logic and symbols. So for all x, there exists y such that x, there exists y such that x bigger than y squared, right? So in fact, if we know about set and we know about the set of real numbers, the set of real numbers is denoted by R. Numbers. We can write a little bit more by for x in R, there exists y in R such that x bigger than y squared, and where R is the set of real number. Okay, now we find the negation of this statement. as we just said before, for own become the axis become for own, and we go from left to right. The statement become the negation of itself, right? So we have there exists x in R such that for own y in R x, so the negation of this one is x less than or equal to y squared. Done. Does that make sense? So we have for own becomes the axis x in R, for own y in R. We have this is not true, meaning that not of this statement, right? So not x bigger than y squared, meaning x is not bigger than y squared, so x is smaller than y squared. Okay, now we found the negations, which is this statement, and now we see that, okay, is this statement true or false? And by this I mean this negation. It is true or false. There exists a real number x such that for all real number y, x is less than or equal to y squared, and it is true. So it's true, so we can take it in example x equal to say 0. So for all, say the x is 0, right? So 0 in R, so 0 in R for all real number y. We have 0 less than or equal to y squared, and this is true for real number. For complex number, we know this is not true, right? Because they I is a complex number, square is -1, is negative. But in our case, we work with the set of real number. Square of any real numbers must be non-negative. So this is true. So here's an example when we find the negation of a statement. Follow the negation rules. Let's do one more example here. A function f is called 1 to 1. Actually, 1 to 1, we have another name called injective function. Right down here, injective. So a function f is called 1 to 1 if for all x and y, f of x equal to f of y implies x equal to y. Let's write it down in terms of logical symbols. So we have for all x and for all y in R. Okay, maybe one small remark here. So this just means that, let's just write down this part only. Okay, for all, this is the same as for all x and for all y. The comma here is for n, for all x and for all y. F of x equal to f of y implies x equal to y. Just remark here, this n is not a logical operation. This is not the same as the other. The n is the n we know. What? For example, we have over here. For example, here, just this n. It's not the same as this one, because this logical operation is between two statements, right? This n is between two statements, it's connecting two statements. But this one is not a statement, it's just for all x and for all y. Doesn't say anything, it's not logical, this just quantifies. So it's not the same as this n. And then when we negate it, we don't just change n to all. Yeah. Just keep it the same for all x, comma, y. There exists x, comma, there exists y. So just a remark that this n and this n is not the same. Okay. So first, let us write down this definition in terms of logical symbol. The function f is equal 1 to 1 if for all x, for all y, f of x equal to f of y implies x equal to y. So this is for all x, for all y, p x y implies q x y. Right? And how do we negate this statement? To change for all to the exist, for all to the exist, and using the negation rule here. If p then q, the negation of this statement is p and not q. Negation. There exists x, there exists y, such that p and not give f of x equal to f of y and I write the n here. X is different from y. Recall that this n and this n is not the same. This is a logical n. There exists x and there exists y such that f of x equal to f of y and x is different from y. So that is this negation is just a definition of a not one-to-one function. Right? So we can write down as a function f is not one-to-one if this condition is satisfied. So now we know the definition of a one-to-one and not one-to-one function. Can we have an example of a not one-to-one function, say? There exists x, there exists y such that they are equal. The values are equal. F of x equal to f of y, but x is different from y. So example of a not injective or not one-to-one function could be this function, say f from R, the set of real number to the set of real number, send x to x squared. This function is not one-to-one. So reason. By definition, what we just did before. There exists x, there exists y. F of x equal to f of y, but x is different from y. So I can choose x is, there exists x equal to, say, 2. Y equal to minus 2. Okay? F of x is 2 squared, right? Which is 4. 4 also minus 2 squared, right? This is f of y. And x is obviously different from y. The value of f of x is the same as the value of f of y. So by definition, this is not onto one function. So that is an example.